Today either. Okay, good morning. This is absolutely wonderful. My wife and I love traveling into Asia, and until about 3 days ago, if you asked her, she would tell you that her favorite city in the world was Hong Kong. We'd been to Singapore before, but having then just spent a bit of time in Hong Kong, a bit of time in Singapore, yesterday she announced that she'd changed her mind, and now her favorite city is Singapore. So, thank you, so I'll be back. Okay, so let me start with a question. How many people here do OO programming? And hold your hand up and keep it up, please. All right. Up, keep it up, keep it up, keep it up. Okay, put it, your hand, no, keep it up. What's wrong? Put your hands up, right? Okay. Put your hand down if you have classes that have public data, public instance variables. Put your hand down if you have classes that have getters and setters. That's about right. Put your hand down if you use inheritance. All right, 1, 2, 3. 3 people do OO programming. Everybody else, you're doing class-based programming, not object-based programming. Yeah? And that's not your fault. It's how you've been taught. When you think about it, when you first start designing an application, what do? You may sketch out a class diagram. Right? That's how you program it. You use frameworks. Any Rails developers here? Okay, 1, 2. That's actually unusual. The frameworks insist that you use things like inheritance when it's the wrong thing to do. So we're trained to do all these bad things. And it's very hard to throw that training out because it's so deeply ingrained in the way we code. So I've been playing around a bit with how to kind of reclaim that purity, how to get back to doing proper OO development. And I've come to the conclusion that the best way of doing that is to use functional languages. But I'm not saying to you, throw away the concepts of OO. I'm just saying, throw away the current implementation. That's a lot better, right? So I have been experimenting with code. And I've been experimenting with a couple of aspects. One, experimenting with code as transformation, of changing state in code. And then the second thing I've been playing with is state itself. How do we represent the state of our program in a way that doesn't couple everything together? Now, my motivation here is I want to produce well-designed code. And to me, there is only one definition of well-designed code. Well-designed code is code that is easy to change. Right? Everything else is irrelevant. If your code is easy to change, then all the other good rules of design fall out from that. You try to avoid duplication, because duplication makes your code hard to change. You try to avoid coupling things together in your code, because that makes it really hard to change. And so I've been looking at how do I represent state in such a way that I can eliminate a lot of that coupling and make my code easier. So let's start off with the idea of code as a transformation. If you went to school, to university, to learn programming, the chances are that somewhere in the first month, someone stood up before a board and drew a picture that looked something like this. How does a computer work, they say? Well, you have the input, and then you have this thing called a processor, and the processor does the stuff, and then it produces output. And along the way, it's probably going to be using some storage device to store the data. And this is how computers worked in the 1960s, and this is kind of like the model that we all have in our heads of what they're doing. I mean, the reality nowadays is like totally different, but it doesn't really matter. This is the model we have in our heads. So let's tidy this up just a little bit, and let's make it more relevant to today. So rather than processor, speak to me. Let's have process. because the same thing applies, right? And rather than having storage, let's think of it as state. So what we have is our programs are simply a process that takes an input, produces an output, and manages state at the same time. So in the process of taking your input and producing your output, you may or may not update some local state to that process. And that's kind of like an object as well. Now, processes can share state, but you only want them to share state if they are effectively the same process, if they're related processes. So you can actually have a chain like this, a chain of transformations where processes are updating a common state or reading from a common state. And of course, you can have multiple sets of this common state. And then if you actually look inside one of those processors, you'll find that we actually have the same thing going on. So inside there, we have the potential to have another set of transformations inside that process. So what we have here is a perfectly viable programming model. We have the ability to have sequences of steps, and we have the ability to have composition. So clearly, we can actually design code this way. We can actually write our programs using this model. And what that is just transformations all the way down. So we start off with our overall program, input goes to output, and we say to ourselves, how can we implement that using nothing more than transformations that sometimes share state? And that's where I got to. So maybe 18 months ago, I started thinking about, can we write a non-trivial, as in any program, as nothing more than a set of single-line transformations? And I set myself the goal of single-line transformations because I wanted to guarantee that I wasn't cheating. So every transformation had to be a single line. And the answer I came up with was yes. I could not find an example that I couldn't do that way. However, it's a stupid thing to do, because it makes your programs really, really verbose and really quite hard to deal with. And I was a bit disappointed, because I really did want to have, this kind of very tidy, very neat thing. So then I changed my criteria somewhat. I said, is it possible to write a non-trivial program where parts of it are nothing more than single-line transformations? And obviously the answer is yes, but it turns out that in this case, it's a really good thing to do. And I'll show you why I think it's a good thing. As Dave said, the thing I'd most like to be doing is programming. And so whenever I have an idea, it's always an excuse to go away and do some coding. So in this case, I tried to come up with a kind of a library or a framework that would let me create these transformations in a nice, easy way. And so I came up with this framework called Diet. It's called Diet because each one of these transformations is actually technically a reduction. So if you apply a series of reductions, it's a diet. And so a diet allows me to create these transformers or reductions, and each one is a series of specifications. And the specifications can share a common state. They don't have to, but they can share a common state. And each specification is no more than that little picture that we saw at the beginning. It's an input that goes to an output, or it's an input that updates the state and then goes to an output. And using just those two things, you can program anything. But the cool thing is that I'm going to program this in a language called Elixir, and Elixir has this thing called pattern matching. Now, it's not like in Python or Java where patterns are to do with regular expressions. It's more like a language where you can have many methods of the same name, and the one it calls depends on the parameters that you give it. Yeah? So you can do that kind of polymorphic pattern matching into methods in languages such as Java. Well, in Elixir, I can do way more powerful pattern matching. So I can match based on the type, but also on the values of the arguments that I pass. And that's what I'm going to do here, and that's called pattern matching. So we have a transformation which consists of a number of these specifications. The specifications match some input, and they produce an output. What then happens is that that output gets fed back in to see if it could match another one of those specifications. And if it does, it runs that, and then again comes back around. And it stops when it cannot find a match. So once you get into one of these reductions, it's going to go reduce, reduce, reduce until it can no longer do anything. At that point, it exits back out again. So, trivial example, and this is like in no way compelling, so please don't judge too harshly. The sum of an empty list is 0, and the sum of any other list that has a head, which is h, and then the tail that's t, is simply h plus the sum of the tail. Yeah? Pretty straightforward. So, you can represent that in diet. Now, ignore the little housekeeping-y stuffs, right? All we really care about is those bottom two lines. And what that's saying is that if my input is the atom sum, that's just basically a placeholder to say, this is what I want you to do. So if it's the atom sum followed by the empty list and the result so far, then the output from that transformation is going to be the result. Otherwise, the output from the transformation is going to be another request to sum the tail of the list, and the result so far is going to be the result so far plus the head. So this is just your normal functional definition of sum. It's recursive, but you'll notice that it's done purely in terms of input and output. There's no actual code in the middle apart from that little result plus h there. And so if you give this a list of 3 elements, the first time through, it's going to say, okay, then it's going to be the head of that list, and the tail is going to split it out on the last line. It's going to do that the next time, and all the while it will build up the result. And then finally, when the list is empty, it will return the result. So I can run that code, and to run one of these reductions, I have something called a stepper. And all a stepper does is it goes in there and it does that pattern match and produces the output, and then does that over and over again until it's finished. So here I create a stepper, and I do it on my module up there, which is example.listsum. The nil, ignore for now. And so if I run my stepper on sum1357, then I get the result 16. This is not earth-shattering. You may be going, okay, Dave, why am I going to all of this extra work to do something as simple as this? Well, let's take it up a step. Let's look at run length encoding. This is where I'm going to take a sequence of values, and if I have 2 or more identical values next to each other, I'm going to compress it down into one value and a count. So this list starts with 2 A's. So my output is going to be, that's a tuple with the braces, A followed by the count, which is 2. And then we have a B, because there's only one B, but there's 4 C's. So the next element is going to be the tuple C, 4. And you look at that and think, hey, I'm a programmer, that's an easy thing to do. Well, I look at that and I say, I'm a programmer, it must be easy. If I try to do that in a regular language, it's about 50-50, I'll get it wrong first time. And the things that go wrong are the kind of weird edge conditions, like whether or not you have the end of a sequence at the end of the list, and this kind of stuff. It's a very good little exercise to run using a conventional programming language because it's very easy to make those little off by 1 errors. But you can specify this really easily using these reductions. So I start off with, I pass in to my reductions the command, I want you to encode this list. And all that's going to do is return another tuple that says, okay, I need somewhere to put the result. So it's going to return a new tuple that includes a space for the result. That's that last parameter. So now we have to handle those 3 element tuples, RLE, list, and the result. So if I have a list that comes in where the first 2 elements are the same, so this is a pattern match, and what happens is the first time it comes across an unbound variable, which is A in this case, it will bind it to the head of the list. At this point, A has a bound value, so the pattern will only match if the second element of the list also equals the value in A. So this will only match a list where the first 2 elements are the same. And what it does is it then replaces that in the input with that tuple of A and 2. So if I have a list that has 2 identical elements, then it'll be replaced by an element and the count. The next thing I have to think about is what happens if my list starts with one of those tuples and is followed by another value which is the same as the value in the tuple. So in this case, if I have a tuple that has A and then some count, and the next element is A, I'm going to replace both of those with a single element, which is A n plus 1. I've increased the count. And then finally, in all other cases, all I have to do is to copy the input to the output. And that takes care of everything. Now, there's only one small issue with this. Now, is if you run it, it will run perfectly well, but the result will be backwards. It'll be reversed. So you have to have one extra little step there, and that is when your list becomes empty, then you have to take the result and reverse it. And if you've done any functional programming, you will guarantee have to come across situations like this where you have to do the reverse. Now, you'll notice there isn't a single if statement in there. There isn't an explicit loop. Basically, there's nothing to go wrong. All you're saying is, if you're given this, produce that. And the cool thing about that is that I can sit here and code that. I live code that sometimes, and it always works. Because you can just look at it and say, yeah, obviously it has to work. Obviously, anytime I have a list that has 2 things the same at the front, I'm going to replace it with that tuple. It just works. How do I know it terminates? Because at every step, it removes one element from the list. So eventually, it has to terminate. There's no option. So in terms of code, it's really, really easy to do. And so if you run that, again, we're going to use that stepper thing, and we feed into it a list, and it's going to go run through and do all of those steps until it finishes, and it finishes when it gets to that thing that does the reverse, and the result that comes back is going to be our run length encoded list. So when I started seeing things like this, I started thinking, okay, there's some merit to this. It's actually kind of a nice way of programming. I don't know if anybody's done any logic programming with languages like Prolog, but if you have, you'll recognize this kind of style of writing using these reductions. It's a very it's just a natural way of thinking about programming. If you can throw away your if statements, it's really good. So then I said, okay, let's give ourselves a bigger challenge, right? So is everybody familiar with the game of hangman? I guess nowadays we should say hang person. So the idea here is you have a word someone's trying to guess. They guess letters. Every time they get it right, you show them where the letter is. And every time they get it wrong, you get one step closer to death. And again, this is not rocket science, but it's a non-trivial to code it up. So I said, how can I do this using this style, using the style of just nothing more than transformations? And to do it, you have to think about state. What is the state of our hangman game? And, I mean, the details don't matter too much, but you know that you're going to need the word that you're trying to guess. You know you're going to have to keep a track of all the letters that have already been used, and you probably have to count the number of turns that are left. You also need what I call the business logic of hangman. That's basically the stuff that does all of the transformations of state. So things like, I'm recording that someone has guessed the letter, or I am counting the number of turns, or I'm saying, has somebody won or not? This is all what I call business logic. It belongs in the model because it's all to do with the state. And then totally separately from the model, I have the transformations. And the transformations are what drives the model. So let's try and make that a bit more concrete. So here is the model. Up the top here, I have the state. So I have word to guess, guess so far, and turns left. Those are those three things I mentioned. And then I have kind of functions that are used to manipulate that state. So have I already used this letter? Or record the fact that I have used this letter. Is this letter in the word to be guessed, et cetera, et cetera. And these typically are just like little one-line functions. They're not part of my overall transformation scheme. They're purely to do with a model. And the cool thing about that is that when I'm doing testing, or more accurately, if I'm doing testing, then I can test this model totally independently. It has nothing to do with hangman. All it is, it's recording the state of a game. And I can use that anywhere I wanted to, but I could definitely test it without having to go through and run a game to test it. It's purely the model. Then I'm going to define my transformations. And in this case, I want my transformations to share a model. Because I want that state to exist between the turns. So for each turn, I'm going to go into my little transformation set and run through it, see what to do. But at the end of it, I want to maintain the state. So I tell my little framework that I want to use hangman model as the state. And because I'm lazy, I'm going to call it HM. So all that's doing is giving me an alias. And inside the actual reductions, I'll be able to reference instances of that state using the name game. This doesn't make too much sense now, but we can have a look at some of the code. Or in fact, that's all of the code. So we're starting off playing our game, and we've already loaded the word into our state. So now what's happening is the player is making guesses. So they are going to make a guess by calling in to the reductions and say, I want to make a move. And they give me the letter to be guessed. So the first thing I do is I transform that input into a 3-element tuple, which still has the move and the make move, but it also is now going to have a Boolean to say, have I already used that letter? So now we're going to try and match make move, move, and then a Boolean. And that next line does just that. Make move, and if the Boolean is true, then my transformation is going to be simply to this value already tried. Nothing else matches already tried here, so our process is going to stop and return already tried back to the caller. But if that's not the case, now we're actually going to start recording the move and doing the actual work. So we're going to transform ourselves into record move, and then the move we want to record. So here, record move needs to update the model. So it calls update model, and then it uses this function HM useLetter. That's one of those functions that we had defined in the model. And it says, record that move in this game. And having updated the state, we're now going to return the value maybe match move. And then maybe match move says, Is this in the letters to be guessed? Yes. In that case, it's a good guess. Otherwise, it's a bad guess, etc., etc. So that is the entire code for a game of hangman. Again, no if statements, no loops. All it is if this, then that. If this, then that. It takes a different way of thinking, but if you can think that way, then it's so much easier to code. I promise you. I've been coding, like, where are we now? 45 years or something stupid. Yes, there were computers back then. And, you know, for me, this is turning out to be what I've been looking for. It really does help me think about my programming. So we kind of talked about that. Let's move on. So here's the interesting thing. And this is why I think functional languages are an interesting approach to doing OO development. The functional lie, although nowadays we're supposed to call it the functional fake news, is that functional programming has no side effects. Right? You've all heard that, right? The big benefit of functional programming is it has no side effects. You can just call a function, it'll always return the same value, therefore it has no side effects. So here's a piece of functional code. Ignore the io.puts at the end there, because that clearly has a side effect. But if you look at just that piece of code, there is a massive, massive, massive side effect that every single piece of code on the planet has that nobody ever talks about. What's the side effect? You don't have to read the code. You can just cross your eyes and say, there's lines of code there, and there's a side effect. The side effect is that the computer is executing it. And on every line of execution, it updates the program counter, the instruction pointer, whatever you want to call it, right? As the program is executing, the computer is going through it, code, instruction by instruction. That is a side effect. It's a massive side effect. Because it's the side effect that says you can't go back in time. It's the side effect that says the state may be immutable, but guess what? It's the only state you've got. I can't swing my state back in time. Again, I think that's a big cause of problems when you're programming. The idea of time is kind of like almost implicit in everything we do. But then it comes and bites us with things like race conditions. And we have to put semaphores and locks and this kind of stuff into our code. We have to use promises to wait for results to come along. All of these kind of things are to do with time. And they're always ugly whenever you have to think of time. So, like I said, this laptop kind of died just before the talk. I'm not 100% sure I've got it set up correctly to do this, but let me just see what happens if I try. And I need my glasses because I'm old. All right. What do we have? Oh, yeah, look at that. That needs to be bigger, doesn't it? So what I'm in here, I'm inside the Elixir shell. This is basically just a thing I can use from the command line, and I can type Elixir code into it. So I could do like 1 + 2, and it says 3, okay? So I can just execute arbitrary Elixir commands. It's like if you've used Ruby, it's like IRB. So let us Actually, I don't need my glasses because I can't see what I'm typing on the screen, and that's far enough away I can see it. So let's create ourselves a new hangman game. So I'm going to say S, that's my stepper, equals stepper.new, and I'm going to call it on the hangman module. And let's pass in the word to guess as wombat, because wombats are the coolest marsupial. Okay, and what comes back is my state, effectively. So now I can start making guesses. So I could say the result and the updated stepper equals stepper.run, and let's make a guess of A. Yeah? And, oh, I'm sorry, that shouldn't be A. That should be make move A. Okay, so, wow, that's a lot of stuff that came back, right? We scroll back up. Oh, I can't scroll. Help. All right. I'm going to show you another trick. What you're looking at here is the various steps that it went through when it was evaluating a make move for A. And that's kind of hard to read. So I created a little debugger. So I can say diet.debug on, and then I can do it on that particular state. And now it tells me that the diet debugger is looking at hangman. I may just shrink the font down just a little. There we go. If I ask for a trace of what's happened so far, then that A goes to A was my initial mistake. But then you can see it's gone through a make move on A. And what that's done is the make move on A initially says, have I already used A? And that comes back false. So now I'm going to do a make move A false, and that's going to say I need to record the move A, then goes maybe match A, because it's already recorded it. Notice there's a little diamond or a triangle next to 2.3. That means that the state has been changed. And if I want to have a look at that, I can just type in 2.3, and you'll see that the A there is highlighted. That shows me the update to the state. So I can tell what's happened. Then it's looked to see if there's a match. There is a match, so it's going to come back with good guess. So my result of this is going to be good guess. And inside the debugger, I can actually run these transitions a little bit more easily. So I can say make move B. And the result comes back good guess. And if I want, I can have a look at the trace. And now I have that 3 series, and it's going through the same series with a B. So I've had A, that was good. I've had B, that was good. So mathematics proves that C should be good as well, right? So let's go back and do C. Oh no, it's a bad guess. I hate that, right? Because I'm perfect. I can't have a bad guess up on the screen like that. I have to fix this. So how do I fix this? Well, in most programming languages, at this point, I've already gone through that. Remember, time is always going forward. My instruction counter is always going forward. So I can't go back and change the past. But when you have a system like this, you can. So I can simply say, hey, let's create a new history, and we'll end it at 2.8. And now you'll notice my prompt has changed to 1. That means I'm in a copy of my history. If I have a look at the trace now, it finishes at 2.8 with a good guess. So now I can start making moves. So W should be good. O should be good. M should be good. With any luck, T. Oh, what am I missing? Sorry? Shout. B. Oh, thank you. Yay, game one. Thank you. Crowdsourcing a game of Hangman. I love it. Okay, so here I have my game and all of the various transitions that got me to that state. And if I want to see details of what's going on, I can have a look at any of these record moves and actually see the change. So at 7.3, for example, I can see that I added the letter B to the guest state. Yeah? But this is just one history. Because we no longer care about time, I can switch back to 0. Whoop, well, I could if I could spell. And now I'm back in the history where I made a bad guess. Because I don't care about time anymore. The practical sides of this are actually quite amazing. First of all, debugging and stuff like that, they get really, really easy. But there's other issues. Say, for example, I have an application that takes a lot of initialization, but once it gets running, it's then going to handle lots of requests. So maybe take a web framework, and a web server. It takes a while to get up. It's got to get database connections and all the rest, but then it can start handling requests, and it'll be running 5, 10, 100 of these things. Well, with this approach, I could do that initialization just once, and then do my clone, and then run independent threads past that. Kind of cool. Anyway, if I was professional, I'd know the key sequences. If you do this kind of coding, you can go back. You can take a history and fork and split it into 2, or 4, or 7, or whatever you want. So this kind of approach gives you a whole bunch of interesting advantages. You can get reusability down to the single line of code if you really, really want to. You can have parallelism at a single line of code. So you can choose to have bits of your thing running in parallel, literally right the way down to the single line of code. As we've seen, I can reload not just code, but I can reload my flow through the code. So I could checkpoint off where I am, and later on, bring my program back to exactly the same state. And clearly, if you've got all of these things, we have world peace. So who needs anything more? So that's part one. And that's to do with programming as transformations. I think that's really, really important. Step 2 is to do with state. How do we represent state? And to look at that, we need to look at Moore's law. And everybody by now knows Moore's law. The number of gates on a wafer of silicon, the most economical number of gates on a wafer of silicon doubles every n months. It doesn't matter whether n is 18 or 24, it is still exponential growth. Is it true? Well, it certainly seems to be, because if you plot the number of transistors on a slab of silicon over time and you use a logarithmic axis, then you get a really very strong fit to a straight line. It's amazing. The very first microprocessor I used was Intel 4004, and I think it's the second blob up on the left-hand side there. And this laptop is like one of the cluster at the top there. It has 1 billion transistors on its processor. I want you to stop and think about that for a second, because we get very blasé about this thing. The processor in just about all of your laptops has 1 billion transistors in it. That's a lot of transistors. However, Moore's law does not apply to processor speed. You'll notice that come about 2005, 2006, we didn't see much improvement in speed. That really bummed me out, because when I started off, every couple of years I could buy a new computer and it would be twice as fast as my old one, sometimes even faster. And then that stopped. And sometimes now I buy a new machine and its clock speed is actually lower than my old machine. And I kind of feel cheated. You know, everyone says, this is more powerful, don't worry. It's slower. Well, it's not slower because we get more cores. So rather than having a 5 gigahertz processor, we have 4 3 gigahertz processors. It's not a bad trade-off. But I got to wondering why that is. Why is it that we've lost the increase in clock speed and instead we have more processors? And so I did a bit of digging around, and it turns out that the power used by basically a slab of silicon goes up by the cube of the clock speed. Now, engineering can explain why it goes up by the square of the clock speed, because each of those little transistors is actually like effectively a MOSFET gate. It's a capacitor. And if you've done any electronics, you know the capacitors charge really quickly to start with, but then get slower and slower and slower. So to switch a capacitor quickly, you have to apply a higher voltage to it. And so you increase the voltage to increase the speed, and power consumption goes up as the square of the voltage. The other term, though, that takes it from a square to a cube is kind of a lot of hand-waving. Because as you make these circuits smaller and smaller, you start getting secondary effects, like the interconnects between the gates get so thin that you actually have problems with getting electrons down them, right? So you have effectively increased resistance, and that burns up power. You get quantum tunneling between the gates because they're so close together, and that uses up power. And there's all these other effects. So this cube thing is not a scientific formula, it's purely empirical, but it seems to work. So here's the cool part. You take a processor and you increase its speed by just 10%. Has anybody here built a gaming computer? Yeah, Fred, yeah, okay. And do you overclock it? Yeah, you overclock it too. And what's your big worry when you overclock it? Heat, heat, okay? Why? Why is heat such a big deal? Well, take a processor and overclock it by 10%. Its power consumption is going to go up by 1.1 cubed, which is effectively 1.3, which means that your power consumption is going up 33%. And what is the end result of power consumption? Heat. And so a mere 10% increase means that your processor is going to be running 33% hotter. My son's built a gaming computer, and the chip on it is maybe, I don't know, that square, right? The heatsink is the size of a toaster. I mean, literally, it's about that by that. It has 4 fans. It has all sorts of, unbelievable, just to keep the thing cool. So heat is the enemy of processors. It's also the enemy of polar bears, because all that heat we're generating is going somewhere. In the United States, data centers use about 3% of the power of the country. So when we say, oh, just throw hardware at it, what we're really doing is taking ice out from underneath that polar bear. So this is why we use multi-cores, because we can do the same thing backwards. We'll take a processor and we'll reduce it down to 70% of its clock speed. So if it's currently running at 1 gigahertz, we'll run it at 700 megahertz. So now what happens to its power? Well, the power drops to 0.7 cubed, which is 34% of what it used to take. So now I can run 3 of these, and I'll have 3 times 70, so I'll have 210% of my initial processing power for exactly the same heat. That's why we do multi-core. Because I can get more and more processor more and more, instructions per second across more processors and not use any more power. And to me, that's a magical thing to be able to do. Speak to me. This is going to be a fun time. Hang on. There we go. Maybe. The problem is that in order to be effective, we actually have to use those processors. If you've got a 16-core machine that's running at 1 gigahertz, then you don't have a 16 gigahertz machine. You have 16 1 gigahertz machines. And as a result, unless you're actually using all of those cores, you're not going to be getting the most out of all this expensive hardware. And because of that, I can guarantee you that our future is going to be parallel. And because it's parallel, it's going to be concurrent. Right? If you're not currently writing parallel code, then you are not currently using the computer to its best advantage. Now, the interesting thing is that Erlang developers have been doing this since 1986, 7, something like that. They have been writing parallel code initially on single processor machines. But they've been doing it because it makes a lot of sense in their particular environment. They wanted to be able to run incredibly efficient code on some complicated hardware, and they wanted it to be incredibly reliable. So they wanted to be able to use multiple processors, not operating system processors, but their own processors, way, way faster. Right? You can create an Erlang process in a matter of microseconds. They use a couple of K of memory each. You compare that to the operating system, it's at least 2 orders of magnitude better in both directions. So Erlang has had this capability for a long time. The trouble is, no one uses Erlang. And why? Because it is a but-ugly language to use. Right? This is, if you ask Emacs to create a skeleton gen server, which is kind of like the specification for one of these processors, it looks like this. Right? Without any of your code at all, there are, I think it's 129 lines of code in there, just boilerplate. I know, admittedly, a lot of it's comments, but it's still boilerplate. And that puts people off. Even if you strip out all the boilerplate and just write a simple server that implements a stack, so it has push and pop operations, it's still that long, which is ridiculous. And again, it puts people off. So Elixir is a programming language that runs on top of the same virtual machine that Erlang uses. So in the same way that Java has the JVM, Erlang has something called the beam. And Elixir runs on top of the beam, and in the same way that any language on the JVM can call into, for example, Java libraries, then Elixir can take advantage of the 30 years worth of Erlang libraries. It's a very deep set of libraries. So when I looked at this, I said, there must be a simpler way. And so that's the second part of this little exercise. I wrote a thing called Jeeves. Jeeves because it helps you make servants. And that is the implementation of a server that implements a stack. What happens is that because in Elixir, the entire language is basically meta-programmed, so things like def to define a function is not actually syntax, it's simply a macro. So my code can actually override that and re-implement def. So it looks through this code and says, okay, you want to export these two functions, and it converts that effectively into this. All right? So by doing that, it's a lot simpler to write these single servers. And to call that, I've got some conventions as well. So if I want to create a new stack that has initially just the value end in it, I can say stack.new end. Then I can do stack.push, open, close, and then I can do a pop. So at this point, Do you notice any similarity with another programming paradigm? This could be Python code, or it could be any other object-oriented language. I'm doing stack.new. Instead of creating an object, I'm creating a process. And then I'm interacting with that object by passing it messages. Here, I can create a named service. So again, it's a background process, but this time I can access it by name. And in that case, I can just say here's a Twitter feed handler. I can just run my Twitter feed and then go and just call it twitterfeed.fetch, twitterfeed.fetch. And that's just going to go and call that single process to do the fetching. Now, maybe I want to get some parallelism in here. So if I just change that one word there, named, changed to pooled, and now it's going to create a pool of these Twitter feed processes, and I can do things in parallel. And it's automatically going to handle load balancing to them and everything else. So what I have here is servers. And each server manages its own state. And the only way of interacting with that server is by sending it messages and receiving messages back in reply. And if you go back and you read about pure object-oriented languages, and particularly if you read about Smalltalk, Alan Kay talks about the essence of object orientation. It's not classes, it's not objects, it's message passing. Right? He emphasizes over and over again that the most important thing is that objects pass messages to each other. Because if you can constrain that to be the only interaction between your objects, you guarantee that there is no coupling between those objects. There's no shared state. It's pure. And this model is exactly that. The only way to talk between these objects, these independent servers, is by sending messages. It is the purest form of OO that we have, and it's done in a functional language. But it's also done in such a way that you can write parallel code automatically. Because in Smalltalk, when they talk about messages, they're really talking about kind of like an abstraction of message, right? This is kind of like, think of it as a message. In Elixir and Erlang, it is a message. It is an inter-process message. It's fast. You measure the time taken in nanoseconds, but it's still an inter-process message. So this is pure OO. So we have state held in our servers. We know that we can write our program using transformations. And those transformations are invoked by message handling, by pattern matches, by message handling. So what we end up with is we have our state, we have our transformations, and so we have objects. And the cool thing about this is that over the last 20, 30 years, we've learned a lot about how to program using objects. We have a whole bunch of rules that make it, not rules, as suggestions on how to structure our code well using objects. One of the key ones in this context, and I think one of the drivers in this context, is the single responsibility principle. Okay? Where a class should only have one reason to change. Same thing here. A server should only have one reason to change. So all of these things we know, we can start applying here. Except design patterns, because design patterns are crap. But apart from that, everything we know, we can apply here. So now we can do object orientation, but in the modern world. And we can do it better than we've ever done before. So this is really the purest form of OO, where an object is a running process, and objects communicate only by messages. And what I take away from this, something as an industry we do really poorly. We need to start learning from the past. We need to look backwards at where we've come from and say, okay, how can we apply this? Erlang is way older than Java, right? But people dismiss it as, oh, it's a good language for writing telephone switches or something. Look back and say, what can I learn from this? How can I apply it? Now, don't worship what you see, just learn from it. Because that way you can synthesize the best of that and the best of now. And of course, the most important thing to do when you're programming is you always have to remember to have fun. So, with that, I am done. Thank you. Time?